So thank you all for sticking around for the last lightning talk session. I think it's been a very productive and fun workshop. We've heard about a lot of great talks and great work. So we're going to start with towards understanding learning in neural networks with linear teachers. And our presenter is Roei Sarussi.
True. Okay. Thank you so much. So I'll share my screen. Okay. Can everybody see the screen? Okay. So hi everyone. My name is Roei Sarussi. I'm very happy to be here. I will present the work towards understanding learning in neural networks with linear teacher. It's a joint work with Alon Brutzkus and Amir Globerson from Tel Aviv University. Basically, we all know that over-parameterized neural networks provide good results from both an optimization and generalization perspective. And we all try to understand why and how that is the case. So we took a simple case study and tried to provide theoretical insights on both of these questions. And the case study is the following. So we have simple linearly separable data distributions. We try to classify a binary classification problem. There are no other distributional assumptions. We take two-layer network with a fixed second layer. So this is the formulation of it. There are K W-type neurons which has a positive sign here, and there are K neurons with a negative signs. We call them U-type neurons, and only the first layer is trained. And this here is a Lick value activation, so a nonlinear one. And we minimize cross-entropy loss, and we try to understand what happens. So before we jump into our theoretical results, some empirical intuition might come in handy. So we look at the networks at convergence in two regimes. The first is the large initialization regime, and the second is the small initialization regime. And what we see at convergence is, first we can see that this is the decision boundary of the networks at convergence, and you can see that we got perfect classification, but if we look at the decision boundary, it's kind of non-smooth and it wiggles around a lot. But if we look at the small initialization, we see we got a perfect linear boundary. If we look at the neurons in the large initialization scale at convergence, we see they are spread out across many directions, while at the small initialization regime, they clustered into two directions. So this is an interesting phenomenon that we've observed, and we try to, that was our lead in theoretically understanding what's going on in the small initialization regime. So this is our theoretical results. So regarding optimization, we have a convergence guarantee that stochastic gradient descent fancy classifier with loss of at most epsilon in order of 1/epsilon² iterations. Regarding inductive bias, so we basically cut it into two parts. The first part is that we show that if we have two neuron clusters, that would yield a linear decision boundary. The second part is showing that under some assumptions on the trajectory, we can prove that gradient flow enters this two neuron cluster state, which therefore yields a linear decision boundary. And this is the inductive bias flow of theoretical flow that we showed. So we'll go over the proof really quickly.
You have 1 more minute.
Thank you. So going over the proof really briefly. So regarding the optimization results, we take ideas from the online perception proof with significant modification to suit our case study, which is logistic loss and nonlinear activations. Regarding the clusterization implies linearity. So this follows from a simple lemma of two neurons networks that we showed that the network with two neurons yields a linear decision boundary. And it's important to note that that's only the decision boundary and not the function itself. So this is the function, it's not linear, but the decision boundary is linear. Regarding our trajectory assumptions, so we are in the late training phase, which is something that follows from our previous optimization results. And regarding our trajectory assumption, so we assume that all the neurons of the same type agree on the data points from some point onwards. And what do we mean by agree? It means that they have same signs dot products with the same data points. So this example right here, we have 3 vectors and they all agree on the data points because they all have positive signs of the dot products with these 3 red points and a negative dot product with this purple one. But if we look at this example right here, these neurons do not agree with each other because the red vector has a negative dot product with the green one, while the 2 others have a positive one. So to conclude, we have a global optimization result that shows that we converge to an arbitrarily low loss training loss. We show that 2 neuron clusters yields a linear classification rule. We show that gradient flow under certain conditions converges to 2 neuron clusters. And we also know that clusterization actually, we observed it in practice, regardless of the theoretical results. So that would be it. And thank you very much for listening. And if anybody has any questions, I'll be very glad to answer.
Thank you very much, Roei. I think we have about a minutes worth of time for questions. So if anyone has a question, please go ahead and ask. So I had one question. Some of the experimental results you were showing were seems related to me to the neural collapse phenomenon that was being talked about earlier today. Is there some connection? Like, can you actually prove that result? Can you prove that result in your framework? Maybe I missed it.
So yeah, there is a connection in the sense what we observe really relates to the neural collapse phenomena. We took the specific case of the linear case, and they held a more generalized frame of work. But empirically, it's the same phenomena. The clustering and the collapsing is a very similar phenomena that the last layer kind of reduces in variability to the similar state. So yeah, empirically, it's a similar phenomena that occurs.
Sure, and you would expect there's kind of some linear separability in the underlying data, just with the right representation. So that makes sense.
Yeah.
Okay, thank you very much. I think we should move on to the next speaker. That's a local convergence theory for mildly over-parameterized two-layer neural networks. And our presenter will be Zhou.
Yeah, thanks. So can you see my screen? Yeah, so yeah, I'll talk about our recent work, a local convergence theory for mildly over-parameterized two-layer neural networks. And this is joint work with my advisor, Rong from Duke University and also Jin from Princeton University. So in this work, we are going to focus on the optimization for neural networks. And in particular, we are going to focus on the following teacher-student setting. So we assume that there's already a good teacher network, and we have enough or basically infinite number of samples. And the student network here is going to share the same architecture of the teacher network, but it is potentially over-parameterized. That is, the number of student neurons is potentially larger than the number of teacher neurons. And we consider the over-parameterization here because empirically the gradient descent may get stuck when we do not over-parameterize the student network. And the data is going to generate by sampling X from a Gaussian distribution and get the output Y from the teacher network with the input X. And the objective function that we're going to optimize is going to be the population square loss. And finally, the goal in this setting is to let the student network to mimic the behavior of the teacher network. Namely, we want them to have similar output. And recently, there are 2 lines of work that shows that the over-parameterization plays a very important role for the optimization for neural networks. So let's compare them in this teacher-student setting. So in this figure here, the blue lines represent the direction of the teacher neuron. The black curves represent the trajectory of the student neurons. And the red points represent their endpoints. So as you can see in this NTK regime, the neurons does not move, just they stay close to the initialization, and this is the same as the theory predict. However, this is not a complete theory for the optimization for neural networks, since in practice, we do observe that neurons can move far away from the initialization. And this is also known as the lazy training in this interesting paper by Chizat et al. On the other hand, in this mean field regime, the student neurons, as you can see, can move far away from the student neurons. And eventually, they will match the direction of the teacher neurons. And moreover, because of this student-teacher matching phenomenon, so in terms of generalization, this regime is preferred. However, just in this mean field, in typical mean field analysis, the existing results usually requires exponentially or infinite number of neurons, and the convergence rate in general case is unknown. So in fact, even in a simpler setting where the initial loss is small, we do not have a good understanding about it. So therefore, in this work, we focus on the local convergence setting and show that when the initial loss is small, the gradient descent can find the global optimum efficiently for a two-layer neural network. And it is, in fact, known that the local convergence result is known for the exact patronization case. By exact patronization, we mean the number of pseudo neurons is the same as the number of teacher neurons. However, we would like to point out that when the network is over-patronized, the situation will become tricky and it will behave, the gradient descent will behave completely different.
Mo, you have a minute left.
Yeah, okay. So here's our results. So given the data generated by the two-layer teacher network with our teacher neuron and the separation delta. So by separation delta here, we mean the angle between two different teacher neurons is at least delta. And then there exists a threshold epsilon 0 that is only polynomially dependent on delta and r, such that when the loss is smaller than this threshold, then the gradient descent will converge to a global optimum with a convergence rate of 1/t. And moreover, at this global optimum, all the pseudo neurons will match the direction of one of the teacher neurons. So here's some remark on our result. So first, the required over-parameterization in our result is met in the sense that as long as the student neuron is at least the number of teacher neuron, our result holds. So it does not matter whether M is just R or M is very large. Also, the threshold here is epsilon 0 is independent of the pseudo network size or the input dimension. So even if the network size or the input dimension is large, the threshold here is still the same. And for future direction, one of the interesting questions is to consider under what cases we can get to the small loss, that is the local convergence setting that we are considering here. So, thank you for your attention, and this is our paper on the archive. Any questions?
That's a very nice talk. Do we have any questions from the audience?
Can you relate this to the results by Liu and Li on convergence for to maximum margin? I think they also have this condition that you have a small enough loss, and then.
Yeah, I guess. Yeah, thanks for question. So I guess there's some difference here because usually in the local convergence for this kind of thing, usually is loss smaller than 1 or n, where n is number of the training samples. But here, basically, in fact, we are considering the population loss, so it is somewhat different from the local convergence for the training loss, I guess.
Thanks.
Yeah, thank you.
Thank you very much, Mo, for the very nice talk. We move on to the next speaker on random kernels of residual architectures, and I think this should be Muthukumar Galanti.
Hi, can you see the slides? Okay, good. So my name is Muthukumar Galanti, and I'm speaking about the paper on random kernels of residual architectures. This is a joint work with Etai Littwin and Lior Wolf. So we start by recalling the analysis of Geiger et al. We have a neural network F trained after T iterations of training, and we have the expected value of the neural network with respect to its initialization, W. And we basically study the fluctuations, which are simply the difference between the trained neural network and its expected value as a function of the width, the depth, and the overall number of trainable parameters in our model. So we know that for a small enough learning rate, each step during the optimization process can be decomposed in the following manner. We can write it simply as a sum of two terms. The first one is proportional to the expected value of the kernel at initialization. So this term is basically of a bounded variance. And the second term is proportional to the difference between the kernel at time t and this expected value of the kernel at initialization. So this term is typically unbounded. So in order to study the fluctuations, we can look at the upper bound on the distance between the kernel at time t and the expected value of the kernel at initialization. So we have, first of all, the distance between kt and k0, and we have the distance between the kernel at initialization and its expected value. So we know by previous applications that the first term is of order 1 over n, and the second term is of order 1 over the square root of n. So basically the second term is more dominant, it is larger, so it is more interesting to study it in order to study the fluctuations. And in order to study the fluctuations of the empirical NTK, we consider the coefficient of variation of the NTK at initialization, which is simply the normalized variance of the kernel, which is a unitless measure of variance. So it has been shown previously by other authors that if we have a vanilla neural network of depth L and width n, then the coefficient of variation of the kernel at initialization on the diagonal scales as exponentially with respect to the ratio between the depth and the width of the neural network. Okay, so in order to have a bounded coefficient of variation, we have to choose the width of the neural network to be proportional to the depth of the neural network. So in this paper, we consider residual and densely connected neural networks, which are depicted in the slide. So, so first of all, for a given residual neural network of depth L and width n, with residual branches of depth m, so each skip connection skips m convolutional or fully connected layers, and we have a trade-off parameter alpha equals 1 over L. So the term, so the trade-off in this slide is 1 over L. And therefore, in this case, the coefficient of variation scales exponentially in terms of the ratio between the skip depth and the width of the neural network. And typically we choose the skip depth to be constant, for example, 2 or 3. So in this case, we have that the coefficient of variation does not depend on the depth of the neural network, and therefore we can choose the width to be a constant. And for dense nets, we have a similar result. We have a dense net of depth L and width n. And then the coefficient of variation scales exponentially with respect to 1 over n. So it is independent on L, and therefore we again can choose the width to be a constant. To validate,
you have 20 seconds left, Tomer.
Okay. So to validate our results, we conducted several experiments. For example, we took a kernel regression for the empirical kernel for finite width neural networks. And we can see that as we increase the depth for a standard neural network, the performance on at test time degrades, and for the other two models, it does not. Yeah, I guess I don't have any more time. So that's it, I guess.
Thank you very much, Tomer. That was really interesting for me. Do we have any questions? It looks like we do have a couple of minutes for questions. So. Okay, maybe let me see if I can give Anastasia's permission to talk.
I think I would be ready now, hopefully.
Anastasia, do you have permission to talk? Would you like to ask your question? Okay, maybe that's not working. So why don't I just go ahead and you can see the questions. Thank you for the great presentation. Can your results be generalized to RNNs as well? Okay, maybe
it was a question. Sorry.
Yeah, that was a question for you. Sorry.
Oh, sorry, I was confused. So it might be interesting to investigate it, but I think that it would be very complicated to use our analysis to extend to RNNs.
Okay, thank you very much, Tomer, for the great talk again. Why don't we move on to Ingo? Were you able to figure out the screen sharing?
Let's see.
Okay, looks like it worked.
Excellent. Okay.
Perfect.
Okay. All right. Yeah, thank you very much. I will talk about a recent result obtained by Nicole, Muecke, and myself. And the title is pretty long, as you see, and it pretty much describes the results we obtained. So the motivation for that is that, of course, we have discussed that today and yesterday, that training large networks is often easier than small ones. Statistical learning theory, at least if applied naively, suggests that the capacity of large neural networks is too large for learning. But we know empirically that the opposite is true. And there are some recent results on some very specific interpolating learning methods, that is learning methods which achieve zero training error, that can learn, meaning that they can achieve risks that are very close to the base risk. And our results consider over-parameterized ReLU DNNs with least squares loss, though binary classification would also be possible. We are interested in convergence to the base risk under minimal conditions on the data generating distribution P. And one of the assumptions we make, however, is that the marginal distribution on the input space X has no discrete parts. And that in particular means that almost surely interpolating methods achieve global minima. Okay, so let's have a look at the results. Here's an informal description. So we consider data sets of size n from a d-dimensional input space. We consider arbitrary DNNs with ReLU activation functions having at least two hidden layers of widths which behave linearly in n and d. At least the first layer behaves linearly in d, the second one is independent of that. And then we can find predictors fd plus and fd minus, which can be represented by such architectures such that the following results hold. Both of these predictors are interpolating, so they obtain zero training error. That is, they are in a global minimum of the optimization landscape. The FD plus, that is the good predictor, is consistent if the sample size goes to infinity. That is, modulo the assumption I've made on the marginal distribution, it can learn for arbitrary data generating distributions. The bad predictor, which is FD minus, fails to learn in a very bad sense. Its risks converge to a very bad risk. And there are also versions of FD plus that achieve min-max optimal rates under usual assumptions for least squares regression, like Hölder continuous target function. I would also like to mention that both predictors FD plus and FD minus can be found constructively using a simple training algorithm. In fact, it's just an initialization algorithm, and that is also pretty cheap. It basically has this runtime requirement you see on the slide. And in fact, if you use the very specific structure of these predictors, and since they are sparsely represented by the neural networks, then you can even find faster training algorithms. Okay, so in other words, we have found a feasible and efficient learning algorithm for over-parameterized deep neural networks that enjoy good learning guarantees, at least if we consider the FD pluses. But on the other hand, there are also regions having a global, having a zero training error. There are global minima, that is, which really fail to learn in a very bad sense. And in particular, this means that achieving a global minimum or zero training error for large DNNs is not directly related to good or bad learning performance of the corresponding predictor. In other words, basically anything can happen. Interestingly, our results also suggest that there are regions in the optimization landscape that are no local or global minima, but they still lead to a good learning behavior. That is, we are not necessarily forced to find global minima to achieve a good generalization. And also it tells us, because we are considering a very specific initialization strategy, that stochastic gradient descent and its analysis should not be isolated in its analysis from the initialization phase. And in fact, we have seen a couple of talks today, for example, and yesterday, that consider very specific initialization regimes, and they are, at least in principle, very different from the ones we have considered in this work. Okay, I think I may have been a little bit too fast. How much time do I have left?
You're actually out of time, Ingo.
Okay. Okay.
But we do have time for some questions. So maybe with questions we can go back.
I was waiting for your time out.
Thank you very much, Ingo. I think did Rob have a question?
Yeah, I had a question, Ingo. Very interesting results. I was wondering if you could just give us a little sense of what's the difference between F plus and F minus. Okay,
so the overall idea is that these two predictors try to mimic certain well-known learning algorithms or their opposite. And then on top of that, we actually construct certain neurons which ensure that, at least locally, they correct not for misclassification, but for bad predictions. So the good predictor tries to mimic, in our proof, a standard histogram rule, whereas the bad predictor tries to mimic the opposite. And
okay, I think, yeah, I see.
That's basically the idea. But it's not necessarily the case that you only have to stick to histograms. It's just the easiest way to prove it.
Right. And are there, apart from, so I think I can see how that might work out. Is that correspond to some sort of qualitative or quantitative difference in some norm of these two functions or something? Is there another, one must be, more wiggly or something, right?
Just a little bit. It depends really on, let's say, if you consider classification, it really depends on the noise level. but the order of wiggliness is probably the same. It's just a matter of constants, actually.
Interesting. Okay, cool. I guess there's a paper. I'll try to find it.
Yeah, the paper has a very different title, but I can give you a link.
Yeah, that would be great.
Yeah, if you could, Ingo, if you could put the link in the chat later, that would be great.
Okay, I'll do so.
Yeah, thank you very much. I'm just gonna maybe if you, Ingo, if you could answer the other questions in the chat, that would be great, because I think we have to move on.
No worries.
Sorry about that. But that was a great talk again. Thank you very much. Very interesting results. Let's go ahead to our next talk on learning and generalization in over-parameterized normalizing flows. And our speaker will be Colin Shah from Microsoft Research.
Hello, can you see my screen?
Yeah.
Hello, I am Colin Shah, and I'll be talking about our work on over-parameterized normalizing flows. So, in recent past few years, there is some considerable progress in analysis of training and generalization of over-parameterized normalizing or over-parameterized neural networks in supervised learning, but it is not the case for the generative models. And for generative models, analysis of over-parameterized neural network is far less known. In generative models, we are given some IID samples from distribution, and we want to learn the distribution. And in our work, we focus on the normalizing flows, which is a generative model. And so I'll give a brief idea about normalizing flows for 1D case. And suppose X is the target random variable whose distribution we want to learn, and Z is the base random variable, which is well understood, any well understood distribution, such as the standard Gaussian or exponential distribution. And Px and Pz are the probability density of X and Z. So normalizing flows try to learn the differentiable and invertible map from X to Z, such that the f of X is Z. So here it means that the capital F is the target function that we want to learn. And in normalizing flow, we are given some IID samples from data distribution, and we want to learn this target function F. And in normalizing flow, we use the maximum likelihood on the training data. I won't go through like specific details because of time constraints. But this objective has this objective has like learner function and the derivative of learner function in the objective. So here, like, how do we represent function f? So based on the representation of the function f, there are two classes of method. One is this constraint normalizing flows. In constraint normalizing flows, we try to represent f function using the neural network, and most of current normalizing flow models use this type of most of normalizing flow models are of this type. And in unconstrained normalizing flow, we represent f prime using so we represent f prime using the neural network. And these names constrained and unconstrained are not standard. So here in constrained normalizing flow, we like f is represented by a neural network, and we impose some constraints on neural network architecture to make function f invertible and differentiable. And in our work, we give some experimental and theoretical evidence that this over-parameterization can hurt the training in constrained normalizing flow. To be specific, like we show that like as we increase the over-parameterization, then training can become slower. So in one experiment, we checked the error on the train and test data after a fixed number of iterations, and we saw that like as we increase number of neurons, then error also increases. So similar trend is we saw similar trend for different initialization, learning rates, and different data sets. Whereas in unconstrained normalizing flows, we represent f prime using a neural network, and if we only need to constrain, like if f prime has positive values, then we know that the function f will be invertible and differentiable. And we need f of x to compute the objective. So
one more minute. Sorry to interrupt.
Okay. So we need f of x to compute the objective, but we can use numerical integration methods to compute f of x from derivative function. And in general, in practice, like gradient-based method works well in the practice. So in theory, results of this unconstrained normalizing flows, we like this is our theoretical result. So fix any epsilon and any data distribution, and suppose we are given some n samples from the data distribution, and suppose capital F is any invertible target function. Then if we are given sufficient large number of hidden neurons, and if we are given sufficient number of samples from the data distribution, and if we train our neural network for sufficient number of steps using Stochastic SGD, then we know that then we prove that with high probability the KL divergence between data distribution and learned distribution is small. So this is our result for 1D unconstrained normalizing flows, and we believe that similar results should hold for like multivariate and unconstrained normalizing flows, and we are working on it. Thanks. If there are any questions, then I can answer.
Thank you very much, Kulin. That was quite interesting. Do we have any questions? Okay, I guess we don't have any questions for Kulin, but thanks for a very nice talk again. And we are going to move on to our next talk by Julian Tachella on the role of over-parameterization and optimization in deep CNN denoisers.
Hi, everyone. Can you see my screen? Okay, so I will present our recent work on trying to understand the role of over-parameterization in CNN denoisers. This is joint work with Yunqi Tang and Mike Davis. And as probably everyone here knows, CNNs offer state-of-the-art performance in multiple imaging tasks, and in particular denoising. But we don't really understand what the neural network is doing to take a noisy image and give us a restored one. So we asked the question of what if some insights, theoretical insights, and in particular the neural tangent kernel ideas, could give us some insight on how this denoising is performed. In particular, we looked at the deep image prior phenomena, where some researchers found out that you can train a neural network with a single corrupted image and minimize the self-supervised loss. And if you early stop the process before the network perfectly fits the noise, you get almost state-of-the-art denoising performance. And this is very surprising because there's no explicit regularization other than early stopping. The network is highly over-parameterized, and the only thing that the network is seeing is the noisy image. First, we analyzed the case of inputting the corrupted image as well as having it for a target. And assuming over-parameterization and gradient descent training, the details you can find in the paper. And when we are in the NTK regime, then the NTK is actually the same as a non-local filter, which is equivalent, which is in the same fashion as very well-known filters such as non-local means, where the weights of these filters are patch similarities, and this function of patch similarities is available in closed form and is given by the NTK. And training a neural network is equivalent to performing iterative image denoising, which is a well-known technique in image processing. Moreover, we can show that it actually denoises because the NTK, so the filter, captures in the leading eigenvectors most of the clean energy of the signals, whereas the noise is distributed in the rest of the eigenvectors. And in particular, we can use our closed form formulas for the CNN NTK and perform denoising directly without the CNN using a low rank representation by an Nystrom, and obtain very similar results to a real gradient descent trained CNN, but much, much faster. However, the deep image prior doesn't really input the corrupted image, but white noise. And in this setting, the NTK theory tells us that the filter, the NTK, doesn't depend on the image in any way, just depends on the IID noise. And this is terrible. So if we look at what filter we get in closed form for vanilla CNN, we just get an ugly filter, which is 1 in the diagonals and 0.25 in the off diagonals. For an autoencoder, it's known that you can get a low pass filter, and this was supposed to explain the good performance. But we know that a low pass filter cannot give us state-of-the-art results. There's no low pass filter that will paint this image so well. And so the question is, where is the gap between theory and practice? What went wrong? And we observed that the main cause was that the deep image prior actually doesn't use gradient descent training, but uses Alon, and that it's an adaptive gradient method. And in this particular optimizer, there's a much larger change than the one we observe in gradient descent from the initialization of the weights. That is order 1. So the NTK dynamics are not really explaining the behavior we see anymore.
Julian, you have 1 more minute.
Okay, so I will show some experiments validating my claims. For example, here we're trying to denoise an image of a house. And if we input noise and we use gradient descent, we are in an NTK regime. We have a low pass filter, it's very bad, it doesn't denoise. Whereas if we input an image, we are in the non-local patch denoiser, where the statistics depend on the image, and actually there's some denoising. But if we use the Adam optimizer, we move very far away from the NTK regime. And even when we input noise and the initialization NTK doesn't depend on the image, we get state-of-the-art performance, and something very similar happens for the image. Finally, we looked at the move of the weights throughout training as a function of the over-parameterization, and we observed that for gradient descent, we have the loss predicted by NTK theory of reduction in the L2 norm, whereas for Adam, we see that the change in L2 norm is order 1, so there's a significant change, even though the L infinity, so each individual weight is changing vanishingly small as we increase the over-parameterization. Thank you very much, and if you are interested, you can check out the paper online, and if you have any questions, please ask.
Thank you very much, Julian. That was a very nice talk. I think we have a nice talk from, nice question from Misha, which was exactly the question I had as well. How do you, Misha, do you want to ask your question?
Sure. Yeah, so how do you think about the difference? What is the difference between Adam and SGT? How do you think about that?
That's a good question, and it's the one we were trying to answer. We don't have the right answers. We try to analyze it from there's different ways of analyzing these, maybe from what is the geometry that is optimizing, is it, you assume that is sine gradient descent. The thing we observe is that it's achieving a much larger change, but the main complexity in analyzing it is that the adaptation and the metric that is optimizing depends on the step size, which is much harder to analyze than the gradient descent, like in the NTK, where the size of the step size can be kind of abstracted out. So yes, there's no exact answer so far.
Okay, thank you, Julian.
Thank you. I think that's a more broadly interesting question outside of deep image priors, to me, at least.
Yes, we're trying to raise the question of that we have to look in this direction, because real problems are using this optimizer, and there's a very large gap of generalization between optimizers.
Okay, thank you very much again, Julian, for a great talk. We're going to actually conclude with our last talk of this session, which is learning and generalization in RNNs. And this is going to be by Abhishek Panigar.
So, okay, so I'll start now. Hi all, I'm Abhishek Panigar. I'm a graduate student in Princeton University, and this is a joint work with Naveen Goel from Microsoft Research India. Okay, so the major motivation of this talk is the widespread success of sequential networks like RNNs, LSTMs, GRUs in NLP tasks like machine translation, question answering, etc. In time series analysis tasks like weather forecasting, and in computer vision tasks like handwriting recognition. However, there is a bit of a lack of theoretical understanding on why such sequential networks can actually learn and generalize on these tasks. And that's what we are trying to answer a bit. So in this talk, we'll be focusing on recurrent neural networks. And before delving into theory, let's look at the structure of the RNNs. So you can think of this network as a network that takes in as a sequence as input and spits out a sequence as output. And each step, what it does is that it takes in as an input token, gets a hidden state as information from all the previous computations, and computes a new hidden state and gives out an output. Technically, the new hidden state is computed as a one hidden layer network on top of the previous hidden state and the current input token, and the output is given as a linear transformation of the hidden state. As you can see, at each and every computation, you are going to use the same parameters WAB. Now, in this talk, we are going to assume two assumptions. First, we are going to assume that the input are coming from some bounded space. And second, the sequence length is always bounded in both the training and the test distributions. Okay, so there are three major aspects of understanding RNNs. First, how expressive is the network under consideration? Second, how well are you optimizing your network using decent algorithms? And third, how well is the learned network generalizing generalizing to the test distribution? What's interesting is that most of the previous work only looked at most two of the three aspects. However, if you want to understand RNN, you need to look at these three together. Up until a recent work, which by Yuanjili and Alon Zhou in 2019, that shows that given that you have, let's say, sufficient number of neurons in your network, then you can learn a concept class using SGD. And the concept class is really simple. It only contains functions that are just sum of function of tokens. And the functions are just smooth functions. This is a figurative way of looking at the concept class. And as you can see, there are like L different functions acting on the tokens, and you just sum them up to get the output. Now, as you can see that this function will have some shortcomings, and you can show that this concept class cannot actually capture simple regular languages like parity. And just to recall, parity is just a set of strings over 0 and 1, which contains even number of ones. And if you have guessed it right, the reason that it cannot capture such language is because parity needs to look at the history together, while this concept class only looks at those tokens independently. Okay, so just to check if RNNs can actually learn some functions better than this concept class, we trained RNN on different regular languages, simple regular languages like Tomita grammar, parity, A star, B star sort of languages. And we found that RNNs can really easily, generalize on all these models, on all these regular languages.
We have about a minute left. Sorry.
Okay. Yeah. So, okay. So now let's try to see if you can improve upon the concept class that was given before. So we saw the following. Given that you are allowed sufficiently large RNNs, then you can efficiently learn the following concept class using SGD. And the concept class is a one-layer hidden network on top of the sequence x1 to xl together. And this one hidden layer network has to contain smooth function, has to behave like a smooth function, polynomial like function. Okay, so this is the figurative way of looking at the concept class that we are showing. So there is a one hidden layer network looking at all the tokens x1 to xl together and giving you an output. And you can use the universality theorem for one hidden layer networks to show that such RNNs can actually approximate all continuous functions of the sequence x1 to xl. Okay, so in summary, we show that RNNs can actually learn better concept classes using STD, and the concept class actually contains all continuous functions of the input sequence. So there are two major open questions in our paper. First is we actually looked at those sequences that are bounded, but can we give a result that actually generalizes to higher length sequence? That's a big question. And second, can we have a theory that analyzes LSTMs and GRUs? Yeah, that's all. Thank you.
Great. Thank you very much, Abhishek. That was very interesting. I think we have about a minute's worth of time for a quick question, if anyone has one. I guess we don't have any questions. It's been a very long and productive day of talks. So thanks to all of you for taking the time out to present, and I've really enjoyed the presentations today.